Hello and welcome to this lecture on writing a MATLAB program for encoding the polar codes. We're going to start with a brief description of how I'll go about doing it and then start writing the code. Okay, so let me take an example of the let's say the easiest example to take is the let's say the n equals 8 code, polar code. So, if n equals 8, if you think of the binary tree representation, you have 8 leaves and then 4 in the next level, right, and then 2 in the next level above that, right. And then finally the root node. And the way encoding happens, you have u1, u2, u3, u4, u5, u6, u7, u8. You need to go up all the way to the top. How do you do that? In the first level, you simply do this u1 plus u2 and then u2. Right, so let me write it a bit differently here so that it's easy. So you have u1 plus u2, u2, and then u3 plus u4, u4, and then u5 plus u6, u6, and then u7 plus u8, u8. Right, so this is what happens after the first level. After the second level, you have u1 plus u2 plus u3 plus u4. Right, basically, and then you have u2 plus u4, and then you have u3 plus u4, u4. Okay, so 2 at a time you combine using the same logic, and then you have u5 plus u6 plus u7 plus u8, u6 plus u8, u7 plus u8, u8, and then finally again you combine the 2. Right, so again you combine. I don't want to write the whole thing out, and you will have x1, x2, x3, x4, x5, x6, x7, x8. These 4 are easy, these 4 are equal to this. These 4 are the XOR of this and this, right. So, together goes here and like that, likewise. Okay. So, this is the logic and this is how we will implement it. We will initially assign the vector x to be equal to u itself and then sort of do in place computations as we go higher and higher. So, we go from here to here and then we will go from here to here and finally, we will go from here to here. Initially, we will assign x to be this and we will process one layer at a time. Okay. And the way I will write my code, I will write it in a general way so that it will work for a general depth. Remember, the depth goes as 0 here, 1 here, 2 here and 3 here. At depth 3, you combine 1 bit at a time, and here you combine so 1 is 2 power 0, think of it as that. You combine here 2 bits, which is 2 power 1, and then here you combine 4 bits, right. So, 4 bits you combine here, which is 2 power 2. Okay. So, the number of bits you combine starts out with being 1 and then keeps getting multiplied by 2. In the next level, you combine 2 bits at a time, next level you combine 4 bits at a time and so on. Okay. But the total number of bits in every level is always 8, right. So, it is always 8 bits after every level, okay, except that you keep combining more and more at a time. Okay. So, that is the idea and we will write the code in this fashion. So, we will start with depth 3. So, there will be a loop on the depths, and for every depth there will be a number of bits that you will combine, and then there will be a horizontal loop which goes through those bits and creates the next update. Okay. So, we will just keep the output vector as the input vector and keep doing in place to get to the final encoding. Okay. So, this is the way I will write my code. Let me get started. Okay. So, before that you need the reliability sequence, and this is an array which is the reliability sequence. It is available here. So, I have taken it from somewhere and put it here. This is the reliability sequence that I had. You see, it starts with 0 and ends with 1023. The standard specifies it with the indices 0 to 1023. Of course, you can add 1 to it to make it go from 1 to 1024. We will do that right away. Okay, so that this gets added. So, that is the reliability sequence. and then so now it's a question of adding the messages, and let me give some room here so that you can see what I'm typing. So one needs to generate messages and start doing the similar operations to before. So for that, maybe I can open one of the so one of the previous things, so that I don't mess up on simple things. So okay, so you need n and k. So let's pick n to be I don't know, we'll pick it as 16 just for starters, and this gives you small n equals 4. Okay, you can write a code if you like to generate that, but this is n equals 4, and then k I need, k maybe we'll take as 8. Okay. So now if you notice, the reliability sequence goes from 1 to 1024, and what is the reliability sequence for 16? Okay. So it turns out I'll find Q1, which is the reliability sequence for this, and the logic for that is quite simple. You take the original reliability sequence and take all the numbers that are less than or equal to 16 in it. Okay. So it's just Q of Q less than or equal to n. Okay. So hopefully this is clear to you. You look at all the values of Q which are less than 16. So you'll start with 0, 1, 2, 4, 6, 16 is not there, 32 is not there, 3, 5 is there, 9 is there, 6 is there, 12 is there, 7 is there, 11 is there, like that. So the same sequence, 13 is there, 14 is there, and then 15 would come somewhere, and that will be the end. Okay. So that's the way the sequence will go. So you start looking at this sequence and pick out only those numbers which are less than 16. So it's sort of efficient in some way, maybe not the most optimized, but efficient in some way. So you get the Q1. Q1 is your reliability sequence. Okay. So once you have the reliability sequence, okay, for the chosen n, you have a certain reliability sequence. Okay. And then after that, you are ready to find the frozen positions, right. So frozen positions are basically Q1 1 colon n minus k, right. So the n minus k, the least reliable n minus k positions are frozen. Okay. So that I think okay, and the message positions are Q1, you could say n minus k plus 1 colon, you can say end. So, okay, so it goes to the last. Okay. So that's the message positions. So we're ready to generate the message. So let's generate a random message. I'll just cut and paste from here so that reduces effort. Should be capital K. Generate k-bit message. Okay, and then I'm going to form this vector u, which is at the base. Okay, so how do you form the vector u? Remember, I'm going to start doing in place computation, so I'll call that the vector x. Okay, so what is my x, or maybe I'll call it u. U is I initially make it 0, 1 comma n. Okay, so it's 0, and then the non-frozen positions u of Q1 of n minus k plus 1, sorry, minus k plus 1 colon end, whatever is not to be frozen, I have to let it be the message. Okay. So this is how it is. The remaining are 0, the frozen are 0, you don't have to do anything more about it. This is the non-frozen positions, so this is assigning message bits. Okay, so one can check these things later on if I have made any mistakes or not. The last last k positions in the reliability sequence are assigned message bits. Okay, so now we are ready to do the computation for the in-place computation for the code words. Okay, so let's do that. I'll put a loop here. So if you remember here, my loop starts at d equals 3. Okay, my loop starts at d equals 3, and here I am combining 1 bit at a time. Okay, so after that I need to go to d equals 2. I'll be combining 2 bits at a time, and then d equals 1. I'll combine 4 bits at a time, and then I'll be done. When I combine 4 bits at a time, I'm done, right? So it depends where you like to start with the d. since the combination happens here, it's best to start with d equals 2. Okay, hopefully you see where I am doing this. So, the combination starts at this point, right. So, you start working at depth 2. So, we can start at d equals 2, and then the number of bits to combine is 1. Okay. So, let me have some variables assigned for that. So, let's start with that. So, I'll say L. So L is a bit M is the number of bits I'm going to combine. That's 1. Okay, number of bits combined, that's good enough. And then I need a loop. I'll have a loop which is on depth, and it will go from n minus 1. Okay, remember this is n equals 4 here. So, n minus 1 down to 0. Okay, and we'll end this loop here, and we'll think about how to start putting in there. Okay, so you have the n minus 1th loop, and m is 1, and so now we can start combining one bit at a time. So, how do you combine the bits? So, you can do I equals 1 colon. Okay, so when I combine one bit, I am going to combine u1 and u2. Okay, so when I is 1, I am combining I and I plus 1, and then my next jump is to I plus 2, right. So, this needs to go as 2 into m colon n. Okay, so this loop is for the combination. Okay, so if I am combining m bits at a time, I start with I go from I to I plus m minus 1, and then the next m bits are I plus m to I plus 2m minus 1. Okay, and then I jump to I plus 2m. Okay, so those are the two things I have to combine. Okay, hopefully that part is clear. Okay, so let's take the first part to be A, which is u of I colon I plus m minus 1. Okay, and then B is the second part, which is u of I plus m colon I plus 2 into m minus 1. Okay, so I've combined this is the first part, this is the second part, and now we are ready to combine. So, u of I colon I plus 2 into m minus 1 is actually mod of a plus b comma 2 and then b. Is that right? So, this is the operation. Okay, so you can see what I am doing here. I go every m step, and then I just simply combine the two to get my the value for the next level. Okay, so once I am done with this, I can multiply m by 2. Okay, number of bits. So this is all right. So when you go from one depth to the next, the number of bits combined doubles. Okay, so you combine one bit at a time at the lowest one. At the next one you combine 2 bit at a time. Finally, by the time you are done, you will be combining the whole thing more or less, and that will give you the output u. Okay, hopefully this is clear. If there is hopefully there is no error, and that should be it. That is it. I mean, this is all that it takes to do encoding for polar codes. There is no major surprises here. So maybe one needs to run this and see what happens. Okay, so let me put a breakpoint here. Let me run it. Change the folder. So you go up to message. So maybe it's good to see what the Q1 is. Okay, so this is my frozen sequence 1, 2, 3, 5, 9, 4, 6, 10, 7, 8, 3, so on, just to see. Remember, I am in debug mode, so you have this k greater than or greater than symbol as the prompt, and Q1 is already assigned, and then I generate my message. Okay, so you can see what the message is. Okay, so it's an 8-bit message 1101 1001. Okay, and then I generate my u. Okay, just to check, u is the all 0. Okay, and then here it is. This is what is assigning u to the code word. So if you see u now, it's going to be so I'll do this. I'll put Q1 and then I'll put u. so that you can see right below Q1 where you got assigned. So, if you see the okay, so the 16th position has gone to 1. Okay, so how do you read this? So, you should look at so the first 8 have to be frozen. So, 1 has to be frozen. Let's read like that. 1 has to be 0, 2 has to be 0, 3 has to be 0, 5 has to be 0, 4 has to be 0, 9 has to be 0. So, 9 comes right here. So, 9 is 0. Okay, and then 10 has to be 0. This is 10. Okay, 9 and 10 are 0, and then 1, 2, 3, 4, 5 are 0. Okay, 6 is also 0. Okay, so 1, 2, 3, 4, 5, 6, and 9, 10 are 0. Okay. What about the remaining positions? If you start with the remaining positions, you start with 7. 7 and 11 have to be 1. Okay. So, 7 is 1, 2, 3, 4. I think this is reading it with Q is a bit confusing. So, maybe I'll also do 1:16 so that we see the actual order. Okay, so it's good to see the actual order also. So you see 1, 2, 3, 4, 5, 6 and 9 and 10 are zeros. Okay, so they've been frozen. You get 0, and then you need 7, 11, 13, 8 to be 1, 1, 0, 1. 7, 11, 13, 8 is 1, 1, 0, 1. Okay, so you can see 7, 11, 13 and 8. Okay, that is 1, 1, 0, 1, and then you need 12, 14, 15, 16 to be 1, 0, 0, 1. So, you see 12, 14, 15, 16 is 1, 0, 0, 1. So, the message bits have been assigned correctly. It was a simple piece of code, but to check it is a bit confusing because these permutations are always confusing. So, you put the permuted sequence there and the original index here to see how the match happens. So, the assignment has happened correctly. There's no problem there. So, now that we have the correct thing, so let's start looking at this. Okay, so you got this, you got this. Okay, and then let's check what A and B are. Okay, so A and B should both be 0. Okay, and U should just not get altered at the end of this. Okay, so what I'll do is I'll run up to this point and finally check. Okay, so that the first step is fully over, and then you can see U. Okay, the original U was here. Okay, and you can see how the processing has happened. 0, 0 went to 0, 0, 0, 0 went to 0, 0, 0, 0 went to 0, 0. 1, 1 became 0, 1. Okay, so we know 1, 1 has to become 0, 1. 0, 0, 0, 0 again, 1, 1 became 0, 1, 0, 0, 0, 0, 0, 1 will become 1, 1. Okay, so the first step has happened very correctly. There is no problem there. So, let us run to the cursor once again so that it finishes the whole of the second loop, and let us check if the second thing got done correctly or not. Now, you look at U. 0, 0, 0, 0 should go to 0, 0, 0, 0, right. So, that is the combination, that is okay. 0, 0, 0, 1 should go to 0, 1, 0, 1, that happened correctly. 0, 0, 0, 1 again should go to 0, 1, 0, 1. 0, 0, 1, 1 should go to 1, 1, 1, 1. Okay. So far so good, it's happened correctly. And then let us run to the cursor once again. This time it will be combining 4 bits at a time. Okay, so previously it was 2 bits at a time, it will combine 4 bits at a time. If you look at 4 bits, these are the 8 bits here. Okay, 0, 0, 0, 0, 0, 1, 0, 1, and then it's going to become 0, 1, 0, 1, 0, 1, 0, 1. Okay, that's correct. And then the next 4 bits at a time is these guys. 0, 1, 0, 1, 1, 1, 1, 1. It's going to become 1, 0, 1, 0, 1, 1, 1, 1. That's also fine. And now we are up to the last step. Now, if you run to the cursor, you should get the last step, and that should be just the overall combination. Okay, so overall combination is 8 at a time, this and this. So, if you XOR, you're going to get 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1. Perfectly fine. So, if everything went fine, if I continue, it should just end. It ended. Okay. So, the U you have is the encoded version, the message is the original message. Okay. That is the simple encoding for polar codes. Okay. So, you can change n to anything else. So, for instance, I can make n as 512 just for fun. The small n will actually be 9. So, one of the things to do is to simply let it be log 2 of n, so that you do not have to keep changing this all the time. K is maybe I can write this down below, so that n and k could be, I do not know, 300. You can do this. So, if you do this, if you encode, you will generate one message and you will encode. Okay. So, it is sort of hard to check when you run it, and you gave the answer. Okay. So, you can see the message if you like. It is a huge 300 bit sequence, and then you can see the code word U, which is the 512 bit sequence. Okay. So, this worked quite fast. It is a pretty neat little code. It is not, there is no major issues in writing up this code. Okay. So, you can fool around with these numbers a little bit and change it around. A few warnings once again about the 5G standard. If you read the 5G standard, there are 3 steps in the polar encoding. Okay. The first step is you take the message bits in and then you append a CRC. Okay. CRC is something I never spoke about in this class. Even for LDPC codes, it is there. There is a CRC addition. CRC is cyclic redundancy check. Some additional bits, about 10 bits or 11 bits or 6 bits or 24 bits or so many other bits that you add to the message for some final protection and for the higher layers to find out if the decoded code word is correct or not. Okay. For that purpose, there is an addition of some CRC bits. Okay. So, that happens, and after the CRC bits are added, the actual polar encoding happens. So, this step here will have a CRC addition before it. So, if I put k equals 300, there will be something called A, which is the number of message bits that are coming in the standard. I think it's also called A. Okay, and then L will be the length of the CRC. I think it's called L in the standard document as well. And then K becomes A plus L. Okay, so you get the overall total number of bits that way. Okay, and then Q and Q1 and all of that is the same. You find the U. Okay, finding the U is exactly like this. Okay, and then after this, there is a rate matching step. Okay, there are a few more bells and whistles in the standard. For instance, there are some block interleavings in the middle, some other type of interleaving in the middle, and some parity bit additions in some few of the cases. I believe in one of the directions, either uplink or downlink. For a short block length, there is some parity addition. The interleaving of the CRC bits is done also for some reason. So, a lot of intermediate steps in the standard. I am skipping all of that as far as this is concerned, because from the coding point of view, this is the most critical step. All the other things come in as a little bit of additions. Okay, the interleaving and parity check additions are also, parity check bits are also related to the coding aspect, but we are not focusing on that in this class. So, later on I will comment on the role they play and point you to some references on how to use them if you like it. Okay, but this is the core of the polar encoder, which is the main part of the code. This is the crux of the code. So, this is how you write the encoding. Okay, so hopefully it was clear to you. It's a simple enough encoding. Okay, so this is the end of this lecture. I'll welcome you to look at this code. It's available for you for download. You can go play around with it, change some parameters, maybe try and make it more efficient. Okay, can you identify one place where it can be made more efficient? I think the inner loop can definitely be saved. You can write one loop free command in MATLAB for that, but maybe the outer loop is a bit more difficult to modify. Okay. All right. Thank you very much. We'll meet again in the next lecture, where we'll start talking about decoders for polar codes.